Um, Good greetings, guys. Huh? Okay, so last week we were looking at Unit 6. Unit 6, which is all about land technologies, if not mistaken. Let me just open Unit 6. Okay, hopefully it will open fast. If not, we'll just continue. Yeah, so Unit 6 was on land technologies. And we looked at the different types of technologies where we have things like star, we have things like ring, we have bus topologies. We also looked at things like carrier sense multiple access with collision detection. So you should know the advantages as well as disadvantages. Today we'll continue, we'll soldier on with handout 7, which we are looking at hardware addressing, as well as flame type identification. When you're sending, let's say a letter, I think we should have looked at this. You specify things like the name of the person you're sending a letter to, the street they stay in, the house number, the city, the town, as well as the country, because that's how this particular recipient will be addressed. So even in computing, you specify a recipient. So when a flame is transmitted across a LAN, the electrical signals carrying the bits reach all stations. However, only the intended recipients must respond. What are we saying? Let me give you a scenario. Okay, let me just do this. So let's say this is a bus. Okay, let me get the pen. So let's say this is a bus topology. A bus topology, remember there's one shared media, and there are computers that connect to that shared media like this. Huh? My drawing may not be straight since I'm using a computer. Okay, there as well. So the round things there are computers. Okay. So as if let's say this is A, this is B, this is C, this is D, this is E. If machine A intends to communicate with machine A, B, with machine C, let me just finish them off so that it may not be confusing to some. So if machine A intends to communicate to machine B, what will happen is this. Machine A will send a packet which will be sent to all workstations. So a copy of what machine A has sent will be sent to all machines in as much as the intended recipient is machine C. So machine A is trying to send a packet. So this packet, the intended recipient is machine C, but as machine A is sending, this packet will be sent to all machines. Simply, that is what we are talking about. Okay, let me just end this. We'll get back to this. Okay. So we are saying when a frame is transmitted across a local area network, the electrical signal carrying the bits reaches all stations. However, only the intended recipient must respond. So if we look at, let's say, our scenario here, we have, okay, we have machine A, B, C, and D. So if a packet is sent, it will be distributed to all of them, but only one of them should be able to receive and respond. So however, only the intended recipient must respond. Each station on the LAN is assigned a unique numeric value, which is called a physical address. a hardware address as well as a media access control address. So each station on a local area network, A, B, C, up to E, or if you have multiple, they will be assigned an address. Sometimes people refer to this address as a physical address. Some books refer to it as a hardware address, as well as a media access control address. Okay, so this address is used in data communication for the sake of uniquely identifying a computer or any node that is on a network. So when communicating, a sender transmits a frame across the local area network. The sender includes the media access control address or the hardware address or the physical address of the intended recipient. Although sharing allows all stations to receive a copy of these bits, each station checks the address of each incoming frame to determine whether it should accept the frame or drop it. So if so, let's go back to this scenario I drew here. If for argument's sake, if the hardware address for this computer is A, the hardware address for this computer is B, the hardware address for this computer is C, and so on and so forth. If this machine intends to communicate to this machine, then in the packet that it will send, okay, let me just get the pen. In a packet that it will send, let's say this is a packet, and there's this portion for the address, just like you put an address on your letters. If the address that is in the address part of the packet is C, immediately B receives this particular frame. It will just drop it. It won't even process it because the address does not match its own address. If C receives this packet, it will check the address that is there, and then it will recognize, say, okay, this is my address. Let me accept this particular packet or frame, and then process it. If D receives the same frame, it won't be able to process it because the address that it has and the address that is in the address size of the address side of the packet are not the same, just the same as E. So in as much as all of them are able to see this packet that has been sent on a shared media, only one of the intended recipients will be able to process it because its address and the address that is in the address that is in the address field of the packet or in the frame are the same. Okay. We move on. So each frame includes two addresses, the intended recipient's address as well as the sender. Remember, a frame is found at layer, at the data link layer. So we are saying each frame will have two addresses. So one address is for the sender, the actual person that is sending. So if this machine was sending a packet on the network, then one of the addresses would have a hardware address of the machine that is sending it. And then the other part of the address for the frame will have the address of the machine where the data is intended to be sent. Why do we have two addresses? Address one, the source address, as well as destination address. The reason being, communication, like we said, communication is a two-way process. Okay, communication is a two-way process. When machine A sends something to machine B, to machine C, sorry, it expects machine C to respond back. So most of the communication processes that are there are synchronous, okay, whereby it's a two-way, or it's full duplex, if I can put it that way. So it's a two-way. Both the sender and receiver should be able to interact. That's the more reason you have these two addresses. Address A, sender's address as well as receiver's address. Immediately you send to this guy, this computer as well is supposed to respond. Then communication has done what? Has taken place. Okay. So each flame, and remember a flame is found at the data link layer, and we are saying each flame has two addresses, one for the sender and the other one for the receiver. How LAN addresses are used to filter packets? The network interface hardware handles all the details of sending and receiving data. What we are referring to as the network interface hardware, it's that point in a computer where you connect a cable. If you remember our computer labs, you find that there is usually a point in a computer where you plug in that network cable. That is what is referred to as the network interface hardware. So this network interface hardware handles all details of sending as well as receiving data. It checks the length of an incoming frame. It checks the CRC to ensure that the bits that are arriving are intact. If you remember CRC, CRC is used for error detection and correction. We looked at this, I think, in handout 5. It also deals with discarding flames that contain errors. So if the CRC is performed and then you find that there's an error, the network interface hardware would discard or drop the flames that are coming through. It also helps when comparing the destination hardware address to a station's MAC address. So the network interface card is what will determine when we go back to this example of ours. So each computer here, just visualize that there's a network interface card because this is a cable and this is another cable. So where the cable and the computer join, there's a network interface card. So this network interface card is what, let me get a pointer. Okay, let me get a lesser pointer. So this network interface card here is what actually helps us in checking, is this flame that is coming meant for me, by checking the destination MAC address. If this doesn't belong to this particular, if this is not intended for this particular machine, then the flame will be dropped. Okay. So if it does not match the stations that were addressed, it gets to be dropped or discarded. A flame addressed to a non-existent station is ignored. So if a flame is sent and it's not the hardware address that is used is not for any of the computers on the network, then none of the machines on the network will be able to respond to it. The network interface hardware can perform the functions of sending as well as receiving flames without using the computer's central processing unit. Each computer has a central processing unit, but as well as the network interface hardware, it also comes with its own central processing unit. So just there as it is, as data is coming through the network interface hardware, it can be scrutinized as well as processed. Okay. These physical addresses come in 3 formats. The various address formats can be grouped into 3 broad categories. We have what we refer to as static physical addresses. Static, which means it doesn't change. So these mostly are the addresses that are on our computers. These, they don't change, they are the same from the time the computer has been manufactured up to the time that you get to buy it. We also have what we refer to as configurable MAC addresses or physical addresses. These are physical addresses that you can use in a simulator. If you've used simulators before, like the one they use for Cisco, which is called Packet Tracer, you find that Packet Tracer comes with what are called configurable physical addresses. You also have addresses that are called dynamic physical addresses. These, they provide a mechanism that automatically assigns a hardware address to a station when the station boots. So the last two, the configurable one and the dynamic one, mostly they are used in simulations. But in real life, we use static physical addresses. Each physical address has a format, and this format has got its own advantage as well as a disadvantage. I've listed the advantages and disadvantages of each. In your notes, you can just get to refer to those. Okay. If I may just highlight on one of the advantages of static physical address, it's the property of permanency, which means this computer will forever have this particular MAC address or physical address. So you don't need to master a physical address. Why? Because it won't change at any time. So if computers or nodes in a network have communicated to this machine before, they should be able to remember to say, if I need to communicate with this particular machine, then I need to use this particular IP address. We have what we call broadcasting as well as multicasting addresses. So when we are looking at these physical addresses, we are saying they come in three formats, which is static, dynamic, as well as configurable. So either of them, let's say if we had to get static physical addresses, static physical addresses can as well be further split into what we call broadcast addresses as well as multicasting addresses. Let's look at broadcasting addresses. Broadcast refers to making a copy of the data available to all others. An example of a topology that uses broadcast addressing is the bus network. If you've seen our bus network there, when A sends to C, the flame will be broadcasted to all the nodes on the network. So with broadcast addressing, broadcast refers to making a copy of the data available to all others. Broadcast has many uses. Most local area networks employ what is called a shared medium. Like I've put across, bus network or bus topology is one of the local area network that employs a shared medium. So they can make broadcasting extremely efficient. All stations are going to receive a copy of the flame. All that is needed for all stations is to extract the frame. Network interface hardware is built to recognize the special broadcast address as well as a station's hardware address. So each network hardware device or network interface hardware comes with let's say a static address that identifies that one particular device on the network, as well as a broadcast address which can be used to communicate to any other node on that network. The network interface hardware address is sometimes classified as unicast address. If a flame arrives with either of the two addresses in its destination, the network interface hardware accepts the flame and delivers a copy to the operating system. We also have an addressing scheme which we call multicasting. So this multicasting is broadcasting. It's a form of broadcasting, but with this, you are looking at broadcasting to only a few or a selected number of machines. So the machines that are in this group, just like a group that you would create, maybe you have this group for the class, but apart from this group for the class, you discover to say there's a smaller group you want to form for just maybe the people that you study with. So we will refer the bigger group as a broadcasting address, and the sub group that you've created for only a few people you study with to refer to what to how multicasting is done. So each session will process a flame and discard those flames that are not relevant to it. So processing and discarding a flame requires computational resources. How can we take advantage of broadcasting without wasting computational resources, either the CPU or the RAM? I've given outlines there, how we can take advantage of that. So just read through, you should be able to just follow through and understand. Okay. Multicasting addresses. How is the network interface hardware programmed to accept some multicast packets and reject others? There is a mechanism, and this mechanism is an extension to the basic addressing scheme. Multicasting extends the addressing scheme by reserving some addresses for multicast. Like I mentioned, you have this bigger group, which is a class. If it's a WhatsApp group, you have this group for everyone in class, and you may have a smaller group for just the people that you talk to. So we can refer to the bigger group as a broadcast group, where if you send everything, it will go to everyone. If you send a message, it will go to everyone. But you can as well have a smaller group whereby if you just want to communicate with individual people, a selected number of individuals, then you can take advantage of that. Identifying packet contents. So the address does not specify what the packet contains. The address just specifies to say this particular flame is intended for this particular host, this particular computer. Many data items use the same representation. A receiver cannot use data in the packet to determine what the packet contains. To inform the receiver about its content, each flame contains additional information that specifies the type of the content. So two methods are used to identify the contents of a flame. If we go back to this flame that I drew here, quite okay, this flame has sender's address as well as destination address, but besides that, there's usually the data that is being sent in this flame. How do you get to know the data that is being sent in this flame? This is now what we are looking at. The two methods that are used to identify the contents of the flame are as follows. We have what we call explicit flame type as well as implicit flame type. So the explicit one specifies which type of information is included in the flame and the values that are used to identify the various flame types. The bits of the flame used to identify the contents is called the flame type field. Such a field is said to be self-identifying. If we look at the explicit flame type, the network interface hardware does not include a field type in each flame. Instead, the flame carries only data. So the sender and the receiver in this instance must agree on the contents of the flame. Okay. Let's just move forward and look at flame headers as well as flame formats. So each LAN technology, let's say Ethernet, wireless, defines its own flame type. Okay, so most LAN technologies define a flame type that consists of two parts. One part, a flame, and then the other part, what we call a packet header. So that contains information such as source and destination addresses, a payload or data area that contains information being sent. In your notes, you'll find that there is figure 2, and figure 2 illustrates the general format of a flame. So a flame will have what we call a flame header, as well as a flame data area or a payload. So a flame header, that's where you find things like destination and source hardware address. And then if you are sending, let's say, a text, this is where your payload or your data will be when you're sending that flame. In most LAN technologies, each field in a flame header has a fixed size and location. All flames used with a technology have the same header. So if you're looking at Ethernet and your network is based on Ethernet, then all the flames will have the same header size. The data area of the flame does not have a fixed size. Based on what you're sending, the size can differ. The amount of data to be sent determines the size of the data area. The hardware sometimes enforces a minimum as well as maximum flame size that can be sent. So if the sender has less than the minimum, the data can be extended with what? Zeros. Below is just an example of a flame. So this figure 3, illustrates the flame format that is used in a technology called Ethernet. An Ethernet flame begins with a header that contains 3 fields. So if you look at this, we have a 64-bit preamble, which is made up of alternating ones and zeros, that allows the receiver's hardware to synchronize with the incoming signal. So this preamble is just used as you are sending. This is where now things like speed will be determined based on this field of a flame. And then from the preamble, you have the destination address, which MAC address, which computer you're trying to communicate with. Then next in the flame, you have a source address. This source address just basically says this particular flame is coming from this particular machine. You have the flame type. The flame type, basically, you're looking at what type of flame is you are trying to send. Does it contain data? Is it a flame that just is used to control communication? And then apart from that, you have also the data that you are sending. And then last but not the least, the error detection and correction part of the flame, which is the CRC. By now, CRC should be something that you've worked with. Okay. You can read more on that, and I'm sure you shouldn't have any problems using networks that do not have self-identifying flames. Okay. Okay, so if you've seen the this type of flame, it has this value too, flame type. So there, that particular flame clearly spells out what it's all about. But as well, we have those that don't have this particular field. So how do you get to know what is being sent? So this is what we are saying, using networks that do not have self-identifying flames. How can computers connected to such a network know the type of data which is contained in a flame? There are 2 possible approaches. The first approach being the sender and receiver need to agree to use a single format for data. So the sender and the receiver, there will be need of that agreement to say, okay, this is what I'm sending, this is what you should expect. The first technique is rarely used because it limits a pair of computers to exactly one form of data. The second approach, the sender and the receiver, they agree to use the first few octets of the data field to store type information, like the other one that we've seen. Okay. The next figure, that is figure 5, will illustrate how the second technique works. So using the second technique raises some questions. Questions like, what size should the type of information be? Who should specify values allowed in the type field and their meaning? Okay. So these steps basically will guide you on how the second one works. So just peruse through and you should be able to get that. Okay, this is how a network or hardware interface address looks like. Okay, it is made up of 4 hexadecimal digits. Okay. Okay, so this last part, I think this is just something that you should read on, but the highlighted part there, just get to read, but don't expect me to bring anything out of there, because I'm just giving you a history of how this came about. So you can just read on that, and we should be good to go. Okay, the same as network analyzer, physical address, as well as flame types. This, just read through. You shouldn't expect anything to come out of that, but it's just for your understanding. So with that being said, unless there are any questions, that has been our unit 7. So if there are any questions, like I've always said, please send them through to the group. And the first thing that we'll do before we go into the next lecture will be to just clarify on the issues that you've raised. So go through the handout, as well as I'll share the video, so that you should be able to just follow through. And if there are any questions, please don't hold them back, but share them so that we may get to interact as well as clarify. Okay, so let's wait for those comments. If not, then the next time we are starting our unit 8.